World Spaceflight News Special Report.
Four-stage engine start. 3, 2, 1. Boosters ignition. And liftoff of Artemis 1. We rise together. Back to the moon and beyond.
Welcome to Flight Day 13 of our 26-day marathon. As Vanessa mentioned, we are looking at adding additional objectives, and the halfway point in this mission allows us and affords us an opportunity to step back and look at what our margins are and where we could be a little smarter to buy down risk and understand the spacecraft's performance for crewed flight on the very next mission. So this halfway point teaches us to number our days so that we can get a heart of wisdom. And adding 7 new objectives above the baseline that we agreed on to further characterize the thermal environment, but also the propulsion system, allows us to again get smarter for crewed flight. In terms of mission status, we are continuing to proceed along the nominal mission, and we passed the halfway point in terms of distance from Earth. We passed the halfway point in terms of time in the mission plan. And in terms of mission objectives, if you look back at Priority 1, which is demonstrate the vehicle at lunar reentry conditions, we bought down half of that on launch day by the rocket delivering us, the Space Launch System rocket delivering us to the point of translunar injection and setting up the initial conditions. We will not realize the second half of Priority 1 until entry, descent, and landing day, as Administrator Nelson described in his opening comments. In terms of priorities 2 and 4, we are 25% complete, so we've got 31 of the 124 baseline objectives complete. We have 37.5% of those objectives in progress, or 46 of the 124, and then 37.5% yet to be started. A lot of those are essentially tied to entry, descent, landing in the post-splashdown time frame. So adding the 7, what we're calling real-time objectives, adds above and beyond that 124 objective content in terms of priorities 2 and 4, and then priority 3, retrieving the spacecraft. We will again achieve that on entry and splashdown and recovery day. We are starting our initial preparations for deployment of the recovery forces out at Naval Base San Diego. Our Exploration Ground Systems-led recovery operations team in the U.S. Navy have begun their preparations for what they call just-in-time training, and they are going to deploy tomorrow for that training, and then come back to shore and then set up for recovery. In terms of the mission management team, we did meet, since the last time I was here to talk to you, we did meet on Tuesday, November the 22nd. It was a non-decisional meeting, 45 minutes, and we just largely statused the progress of the mission. We also met on Wednesday, November the 23rd. Again, that was largely a non-decisional meeting. We did go through the imagery findings to date, and we did discuss those, and there were no imagery findings of consequence through our integrated imagery team. And then the mission management team was off Thursday, November the 24th through Sunday the 27th, largely because the mission is proceeding so well, and none of the anomalies or funnies that are out there are of consequence. We did meet today for 2 hours. It was a decisional meeting. We did close one of our anomaly resolution teams associated with the star trackers and the random access memory built-in test hardware that we're seeing a number of funnies on, and we essentially concluded that the hardware is performing as expected, and this is really just a byproduct of the flight environment. And then we did approve 2 flight rule waivers associated with setting up for the additional flight test objectives, and those will enable us to set up the initial conditions for that.
And if you look at number 11, which is essentially, like I said, halfway into the DRO, that's where Orion's located right now. The imagery was crazy. You saw that the imagery that opening videos clip, and I can tell you, I was in the control center at the console for a majority of those images, the ones that include the Earth and the Moon, and it's really hard to articulate what the feeling is. It's just amazing to be here and seeing that. So it's certainly a pleasure. So I'll just give you kind of a status on where we are. Mike talked a little bit about, we're just clicking off our detailed flight test objectives. Everything's going extremely well. Going so well that we're working with Howard and his team, the engineering team, and the European partners to add more test objectives. If you recall, if you supported the pre-mission briefing, I talked about, the simple question was, why are we flying the flight, or what do we want to try and accomplish? And up to this mission, everything was just test data. So a lot of our models that the engineering team uses for their analysis, they're using just data, figures and test information. Well, the effort that we're doing now to get this real-time performance data from the vehicle and the environment is that valuable data that's going to be put into the test, to update the models to allow us to know exactly how this vehicle is going to operate, and it'll relieve us of a lot of our constraints. A lot of these objectives are going to be, the thermal environment. Try to expand the thermal environment. Right now we're constrained to we can get out of the tail to sun attitude for upwards of 3 hours, but when we come back, we have to wait 10 hours before we can do another excursion. So we're hoping to get more information, get smarter on how the vehicle thermally responds, to give us more flexibility, and that'll be directly beneficial to the future Artemis missions when we're flying the crew. Let's see, for the mission to complete the trajectory, we had planned for 19 translational burns. Up to this point, we've done 9, and we've used every one of Orion's propulsion systems. We've done 3 larger burns greater than 100 feet per second using the orbital maneuvering system, the OMS engine. We've done 3 using the +X, or you'll hear them called as auxiliary thrusters. And those 3 were on the order of less than 9 feet per second. And then we did 3 also using the reaction control system, RCS system, and those were all less than 1 foot per second. And we did 2 of those burns where we actually maneuvered into attitude, the specific attitude, and thrust in a specific direction. And the last one we did was it was a very small burn, but we did it multi-axis, where you don't even have to maneuver to the attitude. So it was a great test of Orion propulsion capabilities. We were going to do a burn today. We call these orbit maintenance burns, but it was a very small burn. We opted not to do it, and a part of the reason also is because when we do our next orbit maintenance number 3, which is in a couple days, we want to. This is one of those test objectives that we're adding, and we want to burn the +X. The auxiliary thrusters for 100 seconds. A lot of that's going to be testing the thrusters themselves. They're rated for much longer than that, but we haven't used it yet for those kind of durations. So we're going to do that, but we're also going to test. I think we want to test some of the pluming on the solar arrays during that time frame as well. So. Just to give you a little highlight on what's coming up. We'll depart the distant retrograde orbit on Thursday, start heading back towards the moon, and then when we have the return powered flyby, that'll be on flight day 20. And that again, when we when we fly by the moon, we'll be 80 miles off the surface. So we should expect to get some more spectacular imagery of the moon as we fly by.
You've heard from Mike and Rick that the spacecraft is operating just tremendously well so far, and we're really happy with its performance overall across all the subsystem areas. And we've been able to accomplish other what we call detailed flight test objectives as well as we've gone along the mission, and we're going to try to accomplish some more in this DRO orbit. And I think it's a testament to not only the spacecraft capabilities and the performance so far of the spacecraft, but also the team. The team has been doing a great job of not only monitoring our spacecraft and looking at some of the funnies and making sure it's performing as expected, but also looking at opportunities to further along test this very important mission and the spacecraft that we have to further future missions and buy down future risks as we put crew on board. And I think that's a great opportunity that we have today in the DRO. I would say that also, I mentioned last time we were here, our performance across the boards continues to be outstanding relative to power we're generating, continue to generate 20% more power than we really need. We still have tremendous amount of propulsive capability or reserves in the prop tanks, excuse me. And we certainly are looking at other performance measurements across the board, across the spacecraft, and those are all going very well.
In terms of risk that's retired, we did talk pre-flight about the Pareto chart, which identifies our top risk drivers. Certainly, micrometeoroid and orbital debris, which is our top risk driver, is in play until we get out of the space environment. But being halfway through the mission puts us roughly halfway through that risk, because it is a function or a byproduct of how long we're in the spaceflight environment. We had other risks associated with first-time flight of the rocket and the overall system performance of the rocket, the integrated avionics and software risk, and RS-25 engine. All of those have been retired. We have a demonstrated rocket. In terms of the spacecraft, some of those have been bought down, but some of them are not going to be retired from a mission standpoint until we get to landing day, specifically the parachute and parachute deploy system, and then the heat shield. So that, again, comes back to our priority one objective. The rest of the risk drivers that come to mind, we certainly have done a much better job of characterizing the overall system performance, and I think we are buying down some of that. So that's kind of a, if you're looking at our top 10 risk drivers, some of them have been retired, some of them are still in play, and some of them won't be realized for good or bad until we get to entry, descent, and splashdown day.
In order to make sure we get enable comm from the vehicle, flight controller and mission control Inco has to send the command to get the onboard comm system configured, and then the ground controller, also flight control position and mission control, coordinates with the deep space network engineers, gives them what the configuration of the vehicle is going to be. Then they actually load the parameters to configure their network to support it. So it's complex. And we've changed things since the beginning of the mission, is to give us more capability, open the bandwidth. So we've added 2 more modes. They're based on data rates, and then we go uncoded, which then doubles our bandwidth. So we're not using a coding scheme to improve our signal to noise ratio, which allows us to actually bring down more data. Do that streaming. When we started streaming the video, it was because we were able to open the bandwidth, which allows us to do file transfers, bring the data off the vehicle, and then also do the streaming video. Well, it was simply a misconfiguration at the deep space network, where they were set up for a data rate that the vehicle was not set up for, and it just going through the troubleshooting process, finally figured that out, and then we recovered. Once we got the right data rate, we recovered the return link.
Yeah, and Eric, just to add a little clarity on this one, is I understand it, Rick, and you can correct me if I'm wrong, we need the spacecraft data rate, the Deep Space Network ground site data rate and the MCC data rate all to be in the same configuration, and we got out of configuration with those just due to kind of some ground-to-ground coordination. Did I get that right?
That's exactly right.
Okay.
Right now, we're looking at 8 avionics boxes across the board from Artemis 1 to bring from the Artemis 1 spacecraft and Artemis 2. Munich and Campos sits on a Orion seat, and so we will be using that seat for Artemis 2 as well. That's a non-avionics system that we would be utilizing on Artemis 2, but nothing else from the spacecraft on Artemis 1 that we would be reusing besides those items I mentioned.
Our recovery operations lead, Melissa Jones, is not on this call, so you might want to confirm some of this with her at a later time, but the ship, we have a well-deck ship that is provided via partnership with the U.S. Navy out of Naval Base San Diego. We will put about 85 NASA and industry partner personnel on the ship to support that operation, and that is above and beyond the ship's standard complement, which is a couple of hundred sailors. We will have deployed from the recovery ship itself at least 4 small boats, what they call small boats. 2 of those will be what they call rigid hull inflatable boats, and then 2 of those will be kind of smaller rafts. And then we'll have 2 helicopters deployed from the flight deck, one to support some of the imagery observations associated with the parachute deploy and splashdown, and another one to support locating the objects that are jettisoned from the spacecraft as it descends, things like the forward bay cover and some of the parachutes as part of the parachute deployment sequence. And then we'll have at least 1 aircraft at a higher altitude capturing imagery. So that's kind of a broad picture of it.
Yeah, right now, good question. Right now, we are getting temperature readings. We're getting, obviously, pressure readings as well inside the cabin, and everything's nominal as we expected. Certainly, what was loaded or what was in the atmosphere when we closed the hatch is what we've got, and our leakage rates are really low. I think it's like 0.03 per day or something like that, PSI per day. So we're really understanding not only just what's inside the cabin, but obviously a lot of measurements we have inside the cabin relative to Munich and Campos. The radiation sensors are all being recorded, so we won't get that data from the cabin until we get back on the ground. I think with the Star Tracker, it's certainly the highest visibility. You know, when we first we had a couple issues where we took, I think, a radiation hit on the Star Tracker itself, and we also had this issue with a bit flip relative RAM where inside the box itself, it has error detection correction automatically. And I think I mentioned in the last press conference, you know, it does, when you have a radiation hit, it may flip a bit in the memory, it auto corrects itself, and it just tells you. And it's a very, very good system that is on a lot of deep space kinds of hardware, avionics hardware. And in this case, when it first tripped, we were getting indications that Star Tracker wasn't performing, and I think through our analysis and of course very detailed look at all the data that we got at that time, we made some decisions obviously to press forward. But it turned out that the Star Tracker was working just beautifully. It was outputting navigation data as expected. This bit trip, we found out through our future or our last few days, several days of hard work by the team, is that this is very anomalous behavior. Many of the Star Trackers in deep space and even in geosynchronous satellites and low Earth orbit satellites have data that shows that they take these kinds of RAM upsets, and so they get auto-corrected and they log it. And so today, when we went to the MMT, we walked through all the data. We showed a lot of detailed in terms of not only from our own program, but from other programs that the Europeans have flown, from other programs that we know about from our sister programs, to learn what they've seen, and the data corroborates what we hypothesized to be. And I think that turned out really well in terms of the Star Tracker performance and understanding what happened with the Star Tracker. So I'll pause there, see if Mike wants to add anything to that
Yeah.
before I answer the next question.
Yeah, Bill, thank you for the question. Howard said it well. The team did a very thorough analysis of the Star Tracker random access memory bits that were being set. And this is a case where leveraging our industrial base and other missions out there, whether they're NASA missions or other missions that use this common set of avionics or very similar design to it, is helping us, and we tap that expertise. In terms of other issues that are out there, we do have one active anomaly resolution team associated with the power conditioning and distribution unit on something called the latching current limiter. It is apparently being uncommanded open, so for some reason these latching current limiters on umbilical 1, uniquely on umbilical 1, there have been a number of occurrences that are being nobody's on the ground commanding these things open. So we're trying to characterize that and understand what the hardware is telling us, and that active anomaly resolution team is working in the background. It is not a high-level concern because we have appropriate levels of redundancy. There's 4 solar array wings, 2 of these per channel, per power channel, and we're recovering from these. We just don't quite understand what the hardware is telling us, and we're expecting an outbrief from that anomaly resolution team in the next couple of days. The other things that are out there, we've talked previously about the coolant loop 1 flow rate being erratic. We believe that there's gas in the fluid, and we're periodically seeing the flow rate drop, and then it comes back up as the gas bubble moves its way through the coolant loop. We also had what I would argue was a gift handed to us from the flight environment. We had the flight control module number 1 had a reset. And that was due to a radiation hit, and it did exactly what it was designed to do. And we have a feature called the cross-channel reset, and the system recovered by itself, and it handled the radiation hit as it was designed. So we're again characterizing the system performance. We're learning from it. We're learning what the hardware is telling us. Some of this is unfamiliar to us in the flight environment, and we're rolling that into all the operations. So I don't know, Rick, if you have anything to add to that.
No, you've covered it well. That cross-channel restart essentially is when a computer goes down and comes back up, it gathers information from the other computers to basically get right back to where it was and get back into a sync with all the other 3 computers. Work just as it's designed.
And I'll answer the last question, or the second question. So we've got, we're returning the Orion IMUs, or inertial measuring units, the GPSRs, which is the receivers for GPS, and then the phase array antennas. So that's the list of items that we are using from Artemis 1 and putting on board Artemis 2.
But as I understand it, we will get to see multiple Apollo landing sites. So
Yeah,
Rick,
we do believe there's a team that's actually actively making the plan, putting the plan together to support the imagery as we fly by the moon. The positive is on the return powered flyby, that area will be lit, so we have the opportunity. We just got to get the vehicle in the right orientation and get the cameras going. We're going to be taking imagery, so and I don't know exactly which sites, but I know on the outbound powered flyby there was 4 sites that were all in the dark, so we didn't capture them. But my expectation is the same 4 will be available this time with the proper lighting conditions.
In terms of the accomplishing what we're calling characterizing the thermal envelope, Orion is, by design, it wants to fly tail to sun. That is for thermal stability of the vehicle, but also from a power production standpoint. And the vehicle, through analysis, is allowed to go up to 20 degrees in either pitch or yaw out of that perfect tail to sun orientation. So what we're doing is we're characterizing the corners of the box, 20 degrees, and doing that. And there's also a thermal recovery time required, as Rick had mentioned earlier, about If we're out of attitude greater than at 20 degrees for more than 3 hours, we have to do a 10-hour tail to sun thermal recovery period before we're allowed to use the orbital maneuvering system. So the waiver was specific to the thermal analysis requirements and the desire to gather some of the data on that thermal envelope expansion, and that is consistent with a test flight. We want to do envelope expansion and validate our models. I don't know, Rick.
I think the second one, you going to cover that one?
I'm trying to remember.
The second one was for the solar array
solar
positioning constraints,
yes.
right? We for the various burns that we do with Orion, we have specific attitudes or positioning that we put the solar array wings, and that's to prevent damage from plume impingement from the reaction control thrusters. And for this 100-second plus X test, we want to put the position of the arrays different than what had been previously analyzed and was considered approved, and that's why we're waiving. And this is to gain the data that we want. That's specifically why we're doing the test. So that's the rationale for that waiver.
Yeah, and thank you for the reminder. So that the specific constraint that we're trying to avoid is not a plume impingement or a load constraint on the solar array wing. It has to do with the radiant heating from the engine that's in proximity to the solar array wing. So those were the two waivers that were approved, and they are specific to these test conditions and specific to the objectives that were set up. These are not just what I'll call generic waivers for operations across the mission, and we did make that clear today.
Mike, would you mind? I'll jump in with a couple fine points relative to that. From a spacecraft perspective, Mike talks about the 20-20-20 degree envelope. I mean, we've already analyzed this as pre-mission. We know that we can operate in these regimes. There were some flight rule constraints relative to the two pieces, the OMZ or the main engine, and then also the star tracker was also. So I think from an overall risk perspective, that's why we talked about pressing forward with this particular objective, is because we feel like through our pre-mission analysis that we're able to operate in those boundaries. We just want to make sure in this real flight environment that we get to those corners of the boxes. So that's one piece, and that's the same for the arrays. The arrays, we've tested and certified them to be in these configurations, although we didn't nominally want to operate them in that because of what we needed to do for the mission. But now as we do the flight test objectives, there's no risk with the hardware in terms of where we want to park these arrays for this test. So I just want to make sure that was clear, Mike.
Yeah, thank you for that, Howard. In terms of the mission length for Artemis 2, we're looking at a 10.5-day crewed flight test. So 4 astronauts will fly a 1-day highly elliptical orbit to basically shake down the life support system and perform a proximity operations demonstration with the upper stage before it is separated at a far distance from Orion. And then at the end of that 1-day high Earth orbit, Orion will essentially perform a mission completion maneuver and use the service module to perform the translunar injection maneuver and put itself on a free return trajectory about 4.5 days out and about 4.5 days back. So it'll be a little over 10 days, and that's our Artemis 2 plan. So.